All right. Okay, so today will be next to talk about before we break it out and then do more individual or group work. So let me see. So first of all, I want to, let's see. I try to reply people's comments on Moodle, but I do want to show you that sometimes the comments are new posts, sometimes it's actually a reply to someone's previous post. So I want to show you that, so you know that. But again, I realized once you, give me a second. Sure. I realized actually, when you get an email notification of a new post being made, I don't think you can tell whether it's posting as a new post or as a reply. So I think you have to go back to the Moodle to figure that out. But I do want to show you just really quick, say for the hierarchical modeling, sorry. For the hierarchical modeling over here, okay, say this is the post that I asked you to do. So I started a new one and Katie posted one. Churro, all of this, I think, an individual post until here, which you see it's very similar, but you just like a little bit dent over here. And that means a specific reply to the previous post, which is, I think, Gavin is trying to reply to Becky, right? Yeah. And then I made further post. So you see one more dent over here, which, I mean, you just need to read a little bit more carefully. But my post is trying to reply to Gavin's with this extra dent. But I did also reply to Becky, which is a little bit back. And then Serenity is this whole other post over here. Okay, so just so you know, because you have to read from the dent over here. And I think, Kendall, I guess you're trying to reply to Serenity. Yeah. Mm-hmm. And then Tony's is a new post, Rachel's new post, and Irene is posting referred to Rachel's questions. I think that's what it was, yeah. And then I replied to, yeah, anyway, I won't go through all of this, but I just want you to know that this is how things are set up. So just be a little bit careful. And I realized, like I said earlier, you won't be able to see that at all in the automatic message from Moodle, like you get the email. I don't think they're gonna show you that this is a new post or replying to someone. You just need to go back and scroll down again, okay? So yeah, it's a little bit unfortunate because I was hoping that, because earlier this morning, I was trying to like reply to people's posts, but then I realized, yeah, everybody got a message. You don't even know if I'm trying to reply just to you. So I would recommend you maybe at the end of the day, like that's what I do. I delete all of the emails first, and then at the end of the day, I go back to Moodle and then go through like the posts all together to see which one I wanted to do and et cetera, et cetera. So again, I just want to tell you that some of the comments here are specific to someone's post, and there's some other general comments I made here and there. So if you get the chance, I think it'd still be nice to have some further interaction. And I also have to say that some, some of the posts I didn't get the chance to reply because those questions I don't think I'm able to, and I already forwarded those to Professor Deloitte to see, I think he will respond at some point, and then I will be able to respond it back. Okay, but at the beginning, I do want to go through some of the ideas because I think some stuff is definitely related to what we have been doing. So let's see. One thing I think it's about what are actually the levels here. So I think this started with Becky's comment, as she wasn't sure whether it's just two levels over here. Like in the original post, I'm talking about like the video itself, because Professor DeLeo, what they did over there is they actually look at two separate models entirely, okay? One is at the group level, so they're only looking at the aggregated data, I think, at the groups, okay? And they analyze the group data using a hierarchical model, so there's that. And then furthermore, they show that, okay, this is, because remember like this 3 graphs that he showed, that's misleading. Yeah, like saying that if you look at the individual level, you're actually going to see a different story, because once you aggregate across individuals in the same group, you average out a lot of information. So he then presented the actual final model, which is at the individual level. But at the individual level, they still have this hierarchical modeling. Okay, so that's how I understood it. So that's why I kind of disagree with Gavin, but we can keep talking about all of this. But now I do want to talk about how is your understanding of hierarchical model at the moment. Say, if you think this is a little bit confusing with learning like that particular example, but you can, if you think that's not straightforward enough, you can talk about the example that we talked about in class, which is the math score. But I do want to get us to start talking a little bit about what is being modeled in the hierarchy. Is it just, because I think one of the misunderstanding before was only if you have group data and individual data at the same time, you'll be able to do this hierarchical modeling. So what do you think of that claim? Is it true? Or you think there's some other ways to do hierarchical modeling that it's not necessary that you have data at both levels or multiple levels? So far we have done just 2 levels of hierarchical modeling, but of course you can keep growing. You can always do more if you want. So those are some thoughts that I want to start talking about. So I would like to spend some time on this, and then later we're gonna move to the code, which is also a key point of what we're doing today. We can break into smaller groups first. So my question is, what is your understanding of hierarchical modeling? Say, in the math score example that we did in class, and as well as in the textbook, that's what they use, as well as maybe make connection to the video that we watched based on what Professor DeVayer had done for that hierarchical model. Okay. So maybe we break into small groups for a little bit and then bring back the class. Maybe talk about what our hierarchy. Let's do one more minute. Okay, so I just brought down some questions here from like people's posts, but I mean we don't have to go through all of them, and some of them I don't think currently we'll be able to answer, especially the later ones, because I think that's more related to the actual model being done. But we do, I think we are able to talk about some of the questions. Say earlier I was just asking the general, what's your understanding of hierarchical modeling? But of course, once you go into it, further questions like, if you want to model your data in a hierarchical way, what do you need? And when you are doing that, what kind of assumptions are you making? And also you can talk about specific example, what are the levels? And then to extend it, how many levels there can be, or just in general, what are the levels? And also one question from Eli, I think, on Moodle is, he doesn't believe there's real Bayesian analysis because he doesn't see it, which, I mean, I tried to answer, I'm still not sure if I'm right, but we can all talk about this because it's just a 20-minute video, and I actually posted a code. I don't know if you noticed on Moodle. I posted Jack's code that Professor DeLeu had used, and just the model part. So, but if you haven't got the chance to do it, like you can check it out later. But anyway, okay, so anyone wants to talk about any of this? Yes?
I just want to ask what you mean by real Bayesian analysis.
Okay, so maybe Eli, you can rephrase your question.
Well, I think you took it out of context.
I know. Sorry. Okay. Okay, we can go back. Go for it. But you can rephrase it. I mean, it's hard to read, but you can. I mean, you're here, so.
Yeah. Basically, so as far as I can tell from the data, from the way that the video presented it, I never saw the calculation of a posterior or even the simulation of one. I guess what you answered is that it's sort of implicit by the fact that we get a line within the curve anyway.
That's how I understood it, but I don't know how you.
But it was interesting to me that it was sort of, I saw where the priors were coming from. I saw where the data model was coming from. I still was struggling a little bit to figure out what the power function represented for sort of Bayesian scheme. But yeah, no, it struck me as interesting because we focused so much in this class on like calculating the posterior and how can we make inference on the posterior, posterior predictive, and everything like that. Is interesting to me to not even see mentioned in the video.
I guess, I mean, one comment I can quickly give is it's a short video, and I think it's trying to convey, I mean, there are two models in the video, and then it's just like only 20 minutes, and then he needs to spend a lot of time building it up anyway. So I think he was, I mean, again, this is actually also, because if you've taken, say, because I know you're in his class, and some of you taken other computer science classes before, like those, I mean, those courses, even if you look at their textbook, if they're trying to do some kind of Bayesian analysis, everything is gonna be very straightforward in a sense that you don't even need to know much about it. You just plug it in the computer, and then you will get the return, like values in that way. But of course, I mean, there are different focus over there. So my understanding of all of that is, say, if you, okay, so I can show you really quick of the, let's see, I have to find it, where did I put it? I probably put it, because I posted the Jack's code. Oh yeah, over here. So it's under the same discussion. Yeah. So I mean, I don't completely understand what it is, but I think so. If you look at the model, I mean, so one good things about the Jack's code or like bugs in general, like all of those packages, it's very straightforward in the way that they, like the way that they write up the model. It's just the way how the model is, and it's in the hierarchy the way that we thought it would be. Say, for example, here, I mean, again, I'm not totally understanding all of this, but say, over here, you can see that at the highest level, you see the response time being modeled as a normal distribution. Okay, so you're doing like RT, and then the bracket I is each observation. And because you're assuming a normal dense stillness, so you use d norm, okay, at least in the language of JAX. And then over here, you're gonna have a like specific mean, right? And a specific, in this case, probably not specific, but a particular variance over here, right? And then at the lower level, which is the power function that they were talking about, okay? Over here, the power function is a times 1 plus, so that was, I think, alpha times 1 plus beta times t to the power of gamma, or something that's what was written in the slide, in the video. So you see that because this is deterministic, this is just a function. Okay. But then of course you put, I don't understand what these are at the moment yet, but I think they have different alpha, beta, gamma. And I believe they'd say they were doing different distributions, all of them. But you can see that like the JAX code is straightforward in that sense that at the highest level, this is the data model. And then within it, it's gonna be a function about the mean. And that was the power function that we saw in the video. And then further on, if you have any other prior distribution that you're applying to all of the parameters, you just put it over there. So that's what I mean. So my understanding of, I still don't quite understand the entire material of how all of the models are set up. And I told you earlier that the data seems to be very messy. I couldn't even get just one. And then I cannot even, we can post it. It's just like, it's not in a cohesive structure at the moment. So we won't be able to try it, unfortunately. But I just want to say that this is actually the JAX code, and I guess it's not really covered in the video. First of all, it's the length of the time, but also just a lot of people out there in their field, they are more interested in the outcome directly. Yeah, but of course, it's a 20-minute video, so I think we shouldn't judge based on that. I think there are a lot of material in it. Yeah, so my understanding is they present the data model, they present all of the priors, they present the hierarchy, and then in the end, they show you all of the plots. And those are the plots about posterior, I'm pretty sure. Yeah, so I think it is like Bayesian analysis over there. It's just kind of like hidden. Yeah, but
it wasn't supposed to be a criticism.
I understand. Yeah. But again, that's the best answer I can give right now. But what do you think, like other people? What do you think of it at the moment? Or any other questions, trying to answer any of the other questions. Mm-hmm.
So we're talking about the data that we have, the school data.
Mm-hmm.
And we were not sure why it was a hierarchical model if we didn't have any sort of levels that we could see. They were just like the meaning of the schools themselves, and they didn't know like individuals and other schools that we could see. So like I don't know what it is that we need to do hierarchical modeling.
Yeah. Okay. Anybody wants to respond to that? Yeah, Tony.
For that one, the schools are like levels, because essentially you expect students within the school to have some school, or like the school affects the students like test scores. And so if we model based off the actual schools, then we can one, translate that to future schools, and two, that's better than modeling based off every school individually, because we can essentially pool all the different school information together, so we have some
So what are the levels there?
well, like the group is each school is like the group. That's like one level hierarchy.
Yeah. So, go ahead. Yeah.
Yeah, just looking at the JAX code, which is
we posted.
response time.
Oh, yeah.
Isn't response time like the first level and then the second level? Even though only
Okay, so
data,
right. Okay. Okay. So first of all, maybe let's go back to the math score example first, and I think I just put out the slide that I had about the model itself. So this is like I had when I was trying to present the levels, okay? But it is not that straightforward. I think say all of the words, in different fields, people use different words anyway. So I do want to just let's spend a little bit more time about thinking about the levels at the moment. And I realize, especially thinking about the video again, I guess because because actually like in that study, they just had 2 separate models, okay? But the 2 separate models happen to be at 2 levels. So I think that started to make people get confused, which I guess in hindsight, I should have thought about it earlier, but back then, I think I wasn't, we were not paying too much attention about that, but I just want to say that in the video, they have 2 separate models. And each of them, like one of them is at the group level data, the other one is at the individual level data, but even just in the group level data, there is a hierarchical model over there. But we can talk about that later because I think with math score example, it's probably easier to think about. So following Tony's comment earlier, so these are the 2 levels. I mean, I define them in this way, but you can think about it in a different way. But at the first level, that will be what the data model is. And it's a level in particular because we're looking at each observation being normally distributed with a school-specific mean and the general variance, like generic variance, which we didn't have a school-specific because this is a special case, like a simpler case. But it is at the school level, which is the group level, because so look at the first line. You're actually not looking at all of the YIJs. You're only looking at the observations of the student score within one school, which is the J school. Okay, so in the same time, you're gonna have capital J of different terms like this. So that's at the, I would say like first level in a sense that because you will have all of them only considered at the school level. Okay, and then the lower level here is not something like extra thing nested within people. It's not like that. It's more about now, because if you believe that the schools that you get actually just a random sample of the whole population, and you believe that all of the school mean actually come from the same school, same mean in some way, or same distribution in some way, so that would be the second level. So the level is not how the data arise. But of course, if the data arises in this hierarchical way, you're just gonna have more levels. That's how I understood all of this. So say here, even though you only have student score, which is this individual level, but because you will be able, you don't have school level data, say like school average, you don't have that, but you have people nested in school. And then if you believe that students in the same school gonna be following this, the score of them, gonna be following a normal distribution with the school mean, and then we also believe that all of the means of each school gonna follow a grand general normal distribution over there, that will be a hierarchical model. Does that make sense? Yeah, so I think, yeah, again, I guess this morning when I was trying to answer those questions in Moodle, I started to realize because of the video, like the way that the data was presented, it was a little bit maybe a little bit misleading, but we can keep talking about all of this as well. So any other comments, say, or like, do any of this? Yes, Nick?
Just a question. If we have a data, or for example, some kids test score and which school they're from, and then the model is hierarchically saying that each school on average has different test score. Can we test whether the means of different schools is significantly different from the average among all schools? So then even if there needs to be a hierarchical model in the first place.
Okay. So you're saying, so there are 2 parts of the question, is that right? Like whether you should use hierarchical, and then if you do, how can you make inference whether each of the school mean is different from the grand means, like the mean over here? Okay. Oh, that's a hard question. What do you think? Say, now you have run all of this. So this is like, again, different, I wouldn't say different, like something that we haven't spent too much time looking at. We're like what people have been talking about earlier, we're so focused on how to make the code work, how to analyze them, etc. But the actual analyzing part at the end, you were pretty much just following what, say, like the homework question asked you to do, but you didn't get the chance to think too much about why you're doing this. But next question is, what if we have run all of the gives and we get a bunch of draws from this give sampler? How can you make the inference whether all of the mean, say all of the mu j, I guess, over here, is different from the mu? Is that what you're trying to ask? Different from the mu in this notation?
Yeah, or whether the difference of mu j from mu is significant.
Mm-hmm. So that's a very specific, I think that's a very frequentist style question that, because you will use the term, say like, significantly different or not. I mean, in frequentist approach, you can do a hypothesis testing over there, right? But now, imagine you just, I mean, you have a bunch of draws, say for each of the mu j. So if you have run the code, you realize that if I run it for s, capital S number of times, say like 10,000, and if I do all of the thinning and like all of the burning, say I have 500 draws for each. So in the end, what you're gonna have? You're gonna have 500 draws of each mu j, 500 draws of mu, 500 draws of tau square. In this notation, I'm trying to refer to this, and 500 draws of sigma square, right? So that's what you're gonna have in your Gibbs sampler, out of the Gibbs sampler. So how you can, yeah, how can you test that? What do you think? You have 500 draws of, say, mu1 and mu2, say, between two schools. I guess one thing you can do is return the posterior probability of looking at whether one larger than the other one. And that's very typical of the homework questions, like from the textbook. Okay, so I think I would just say, like, think a little bit like more based on, you just don't blindly follow what they ask you to do. I mean, it is not easy already, but I'm just saying that, like, once you look at the questions, try to think behind what they're trying to, what kind of inference they're trying to do when they ask you a question like that. But any other comments about Nick's question? So he was saying, how can we test all of the mu j being different from mu or not? Mm-hmm. Yeah. Mm-hmm.
Or from the individual level data, you're trying to figure out what mu and tau squared are, and then using that, you can get the estimates for mu j for mu j for each group. And so essentially, if the estimates are like very varying, you'll just have a larger tau square and show that the distribution has greater variance amongst groups. And so there's not exactly like the statistical significance involved with creating that distribution.
So if, for example, you realize that the tau square is kind of low, then you would say that there's not a big difference between groups?
Yes.
Okay.
There's a small difference.
So that gets into a really interesting point here. So what Nick is asking is at the second level, say, because now in the model, we assume that mu j follows a normal distribution with the same mean, mu, and the same variance, tau square. But in addition, like, in order to think about whether all of the mu j's are different from each other or not, you do have like 500 draws in the end. I guess you can do like maybe school-specific comparison. But if you think about this assumption here, we're assuming that it's going to be following a normal distribution. So this tau square, which is the variance of this normal distribution, actually means something, right? So like you have 500 draws of tau square in the end, and you will be, so that will be your posterior, approximation of the posterior of this tau square. And what Tony was saying, that I guess in the frequentist approach as well, it makes more sense to actually think about tau square itself, because tau square measures the variance, measures the variability of the normal distribution that all of the mu j follows. So do they have like a threshold? Like say, oh, if it's above some number, it's going to be significant, or like not using the term, but some other way to do it?
They're not exactly worried about significance, but basically that's the variance there kind of tells you how much information the groups give you. So essentially, that's actually, yeah, essentially it's not, they don't use that for significance. Like they actually don't worry about significance very much with multi-level modeling. But it's more so just kind of giving you an indication of what the groups do.
Right, so if tau square is large in the posterior, say, or like in the frequent, like whatever, like when you make the inference, if tau square is large, then in the model setup, that's just telling us that the means of each school actually vary a lot, even though we put it like a normal distribution. So I think that provides another aspect of all of this, because say, usually, because I think for a lot of times, like the Bayesian analysis, because you have all of the draws, you can always summarize them in this way or another way, and you feel very powerful. But a lot of the time, you should like step back to think about what are the parameters are. And I understand, like, because of the difficulty level of all of this material that will be going through a lot of times, like people just exhausted figuring out the give sampler and then how to derive it, etc., how to code it. But like I said now, because starting from now, we're gonna move to JAX, which can do all of those for you. So wish, like, everybody, including me as well, should start thinking about what are the implications of the models. Don't worry too much about the coding and the derivations now, because like I said, for give sampler is still good because the full conditional are recognizable. A lot of times, if the model gets complicated, you cannot recognize it. And it's gonna be much more complicated sampling algorithm out there that people study and do research about. But for our class, I decided not to go too much into that because it's just mechanical stuff that you have to follow the steps and do this and code it up. But because JAX and bugs, all of those packages can do that for you, I would like all of us to think through, say in this case, our next question is, oh, I want to know about the variability of the mu j, what can I do? You have the draws, but also you have this tau square, which measures the variability. And that should give you some idea in the posterior sense of how things are varying. Okay, make sense? Cool, anything else? The assumptions, I put down the assumptions. I just want to make sure that people don't just blindly trying to do hierarchical modeling. Say here, the way that we put it in this way, at each level, you put a normal distribution. And whenever you put a distribution, you're making assumption of how things are behaving or how you believe the model, like how you believe the data arise or like should follow. So in this case, at the first level, you're saying that within each school, all of the observations are normal distribution. Okay? And second level, which I think is more important to think about the assumption in this case, is you assume that all of the school means follow a particular normal distribution that you try to make inference about. So that's a really strong assumption. And because on the top, it's IID. It's just, on the top over here, it's pretty much just IID within each school. And we're pretty familiar with that kind of setup. You think all the observations are exchangeable, so you can do this. But once you move to the second level over here, I think the assumption of believing that each school, the mean of each school actually follows the same normal distribution is actually very strong. And you need to, I don't think say like any kind of data, you are able to do that. Because in theory, say in this case, because it's the mean of the math score, okay? And they were believing that because the school, like the 100 schools that we get, is just a random sample of, I don't know, thousands of schools out there in the US. And then they believe that they should have a true normal distribution about the mean somewhere. So you can do something like this. Okay? Yeah, Eli?
And it's also probably not true in the example of schools.
What do you think?
Just because schools have been in the public school system in the United States is like not at all distributed in terms of the allocation of funding.
Exactly. Yeah. So that's a great point. So I would think if you have extra information about all of the schools, you can create one layer of hierarchy over there. In a sense that, say, if there's some other measures, so I was trying to actually reply to Rachel's questions about, so Rachel, can you talk a little bit more about the data set that you're doing?
Yeah, so I want to estimate the loss cost of insurance companies, especially auto insurance. And so I have the premiums and the payments, but it's for each individual insurance company, so all of their payments and all of their premiums. So I was kind of just curious if I only have data from one level, can I still use our hierarchical modeling?
Yeah. So I just came up with one solution in that way, like, and similar, like I brought this up because I think it's related. So in that sense, say if you have extra information about the companies, and then say I just came up with, I don't know if it's true, but say if you have like different size of the companies, like small, medium, and large, and because you probably believe those companies are gonna have different means or the different behaviors. So different type of companies, say like if you have, based on the size, you have 3 different groups. If you believe that, and if you believe that that kind of hierarchy can be set up in that way, then that will be a way to introduce the hierarchy. And similar to Eli's point over, like just now, because Eli pointed out that because the US public school system operates in a very enormous way that you have much variability across all the schools. So the second level probably doesn't make sense, because you shouldn't believe that all of the mean scores of each public school that you can get is going to follow the same normal distribution. But if you, sorry, go ahead, no.
I was wondering, could you still, I mean, it doesn't necessarily have to be normal.
Oh, yeah. Yeah, there's, exactly, yeah. Yeah, so you can do, normal, you can do a mixture of normal, which we're so familiar with right now, and also other distributions that you can do, right? So earlier I was trying to say that you can introduce one more layer for the hierarchy, because say if you identify 4 kinds of schools, public schools of course, based on, I don't know, their funding level, other aspects of things, it probably makes more sense to model that way anyway, yeah. So I don't want everybody to be feel so restricted. Oh, I know I have to do hierarchical modeling, so I have to figure out whether it's going to be a good use of the model itself. You really should think about the problem at hand. And if it doesn't make sense, just don't do it. It's not necessary that you have to do hierarchical model anyway. Yeah.
You still have to have the schools be exchangeable, even if you wanted to model them differently. So wouldn't that be complicated?
Yeah.
You need to add a latent variable or something like this.
Earlier, I was saying if you have one extra layer of the hierarchy, I was just trying to say that now, say in between here, say in between these 2 levels, you have a 1.5 level over there, trying to have different types of schools.
Right.
Yeah, but I don't think it's late. Okay, so as you can see, there's so many ways you can do it. You can add one more layer over here, or add a latent variable in the sense that you let the data decide. I believe there are 4 types of schools out there. And based on whatever that is, we don't know yet. But that's similar to the mixture model that we have done before. Okay? All right. Okay, maybe just, let's see. Anything else? I mean, the last 2 questions, I think, one is from Tony, the other one is from Katie. I just forward this to Professor Dilo. I don't know how to answer them. My guess, so the first, number 5, I think is from Tony. I talked to Professor Dilo before. My understanding is it's actually like a latent variable over there that you're gonna switch. Once you hit some threshold, you're gonna switch to the other curve. Yeah, but I don't know exactly how that is set up. So hopefully when he gets back to me, if he has some explanation over there, I will pass it along. And for number 6 from Katie, I actually don't know. I mean, it makes sense to me, but I don't know, say exactly. So, okay, so Katie's question is, because we expect people to not be able to predict letters such as N, because it's harder opposed to I or W, we should assign, or would assign different parameters to the priors in the models for those lines. So, which I don't know the answer. And if any one of you want to give a quick comment, we can welcome that. If not, I can wait until Professor Diller gets back to me. Because my understanding as well is they do put the same priors for all of the parameters for all of the different letters, right? So does that make sense?
Isn't it similar to the question you're talking about, schools are different, some schools, the better schools?
Yeah, exactly. Right. Yeah, so that's true. So that's what I was wondering about as well, because back then the group is about the letters, right? So all of the scores are the response time, right? They use a normal, and then there's power function, etc. So that's the more technical part over there. But the groups over there are about the different letters, okay? So it's about the N, the W, and the I. And I think I just don't know exactly, but I do think, for me, I would think you can argue that I should just assign totally separate things. Or if you just think of them as different groups, and then you believe that they probably follow the same, then you can do that.
I think probably the reason why they're all the same is to avoid overfitting the data. I think that if I understood correctly, the model is tuning them, it's leaving them as free parameters and tuning them. And so I think leaving all of those NI and W as unique parameters would make the amount of the space of the model to predict really broad.
Right. So the overfitting, we sometimes talk about this, it's talking about, say, so try not to specify a model with too many parameters, because even, yeah, you can do it. You can probably fit it really well. But once you move the same model to a different data set, it might not work well because you overfit, you use too many parameters to fit the current data set at hand. So that might be an argument there as well. And to me, actually, I mean, maybe I'm missing things, but like for number 6, my understanding is at the group level, they probably don't have many data points either, because at the group level, they're doing average of all of the individuals in the groups. Yeah. So probably that also restrict in a sense of the number of parameters you will be able to specify. But again, I will definitely like pass along when he gets back to me. Okay. Okay. Yeah, there's some other questions here and there. Like I think I sent 5 or 6 over. So, but like I will let people know. But again, like I said, when I respond on Moodle, it's just a little bit weird. You have to see whether I'm responding to one thread or I'm starting a new one. So once everything pulled down, I would just probably send a summary in the end so you can read through. Okay? All right, cool. So the rest of this class is I was hoping to help all of you at least install JAX. It's not that straightforward because I know some people got into trouble here and there. So if you have, yeah, since you have your laptop, please go to Moodle and then go down here, the R resources. And if you have done, like if you have successfully downloaded JAX, you can help your neighbor so we can be more efficient. But the general guideline is go to R resources, and then you click R resources share. So I have one post over there, download and install JAX. Okay, so you click over there. So there are multiple things. They have the JAX project page, which you don't have to worry about now, but if you have any questions, you might want to go to the project page to look for like solutions and stuff. But for downloading, you should copy this line, which is choose the one, like to download and install. Sorry, you copy that and then go to a browser. So once you get there, you're gonna see like a list like this. Okay? So you should choose the one for your operating system. Okay? So I think most of it is Windows, and I mean Mac and Windows say over here. So if it's Mac, you click that, and then you should download the most updated ones, which is 4.3.0. Okay? So click that, you would download. I won't do it again because otherwise it's going to overwrite what I have. But I will walk around to make sure that you all get it. There's some tricky part about this because I think your operating system might not allow you to install. There's a way that you can force it. So that's something I would like to help out. And once you've done that, you go to R. So just hold. It's gonna ask you to go ahead. Yeah, so this is not okay. You download what I said. Yeah. Yeah. Okay. You have to install it. Yeah. Okay. Yeah. And then you got it.
Is there a way to check?
You can install it requires.
I required it.
Did you download like one?
Yeah.
Okay. Let's go. So go to, okay, so let me just show everybody else who has done it. So you can go to, because I post the code, and the code is actually under here. So it's under Bayesian Hierarchical Modeling. It's the 4th document. Hierarchical Model for Math Score. I have parenthesis RJAX, so that's the R code you download to your laptop. And the last one is the data set, so you can start playing with it. Okay, so read through the JAX code, let me know what you think. Oh, okay. Oh, you can download, okay. It should be RJAX. You go to Uno, there's JAX, like article of the JAX. Oh, that's right. It's easy enough.
Easy to say.
Yeah. Okay. Yeah, that's what we do. So don't unfold it. Oh, you would. You would. No, you're not on to this point. It's actually this writing the model. You wouldn't see anything and not. Yeah, that's it. And then you just run it. Yeah, and then run it. Yeah. Cancel. Oh, okay. Okay. It can actually delete.
That's really good.
Install. No, just that. Just the first. Oh, yeah, this one first. Okay. Okay. Do you install this?
I think so.
Can you run the required? Okay, and then keep going. You probably good.
I loaded it, I downloaded it on my computer, but I'm still, it's now on. So I need to put it on here. I mean, it already, like installed,
Oh, you saw it?
like when
You did this? Oh, okay.
Yeah, I asked you.
Oh, no, you don't have to do it. So once you do this. It's just, I mean, because you actually load it again, so you don't have to try to say that in this case. So this is just general, that you should install it once, but later you should clean it out.
Oh, so this is what our thing from here.
Yeah.
Just like, so I have to have this data.
Oh, yeah. Oh,
So it's a number for one.
Go to the top one, go to the small one.
oh, sorry. It's not that. We go to download the article, this is the general. That's the JAX.
Oh, so it's, well, but it's here.
Maybe don't do this. Go to download all that. Yeah, so that's what I said.
So, do, I see. Okay.
Yeah, so that is.
There.
No. Oh, wait, it was in our studio? On the server, that probably doesn't work. So
Those things.
you will need to, yeah, because not like on the server, like unless the server has been hired, you cannot do it. So
That's why I was.
Okay, so in this case, we do
Hey.
yeah, so you, yeah, but I would say maybe get ours here. Yeah, so I would say Cristiano Ronaldo. Yeah. Right, so for those of you who installed JAX already, like this is the code that you should download to play with. That was the JAX code that I came up with for the particular example, but I set, certain results I cannot replicate, so you might want to figure that out. But let me go one more round to make sure everybody has it, then I want to talk as a whole class about the code itself. Wonderful, you have to pick everything. Yeah, yeah, I will have to, yeah, so only one here. And there are one down there. Yeah, you need to have it there. That's just writing them off. Yeah, so anything in the code, do not delete. If you see my quotation marks, it's there for some reason, don't delete it. Yeah. I have to, yeah, I will explain it once I help everybody figure it out. Yeah. Don't delete the quotation marks, you should keep everything there. Okay? All right, so yeah, I do want to okay, so let me spend some time talk about the JAX code a little bit, and because I noticed some people are trying to delete this and that, don't do it. It's there for some reason, and I want to explain that one by one. So, okay, so if you can just pay attention, to the screen for now, just a little bit. It should be really fast. So on the top, it's install the packages, and then, so you can use library or require, whichever, that's trying to load the libraries, okay? So I saw good practice when I saw people installing it. So once you install the packages once, you can just comment it out or delete, because you don't want to install it multiple times. But I put it there for the first time because you had to do it for the first time, but for the future, because otherwise you would see that R saying that, oh, like warning message, do you want to update your whatever package? Yeah, so don't do that. But once you get that ready, now I can comment those lines out, and then I can start require the two package over here. Okay, so you see, once I run it, it's gonna require RJAX or require Coda because they're installed already. It's just straightforward, they run. Okay. All right, so for the first part of this, I wrote load data set. So you can run all of them all together. The names, you will see that later is corresponding to the names I use in the model. Okay, so this is the same data set, the math score. So I have my data as the data set name, and then Y is the math score, which is the response. Okay, small y, that's the second line. The school is the school indicator. That's also the name of the variable back in the data set. So if you go to my data over here, you see that it's two columns, right? School and math score. So I try to extract those information out, name one of them to be Y, which is the school score, and the other one to be school. And this capital N is just the number of observations. Okay, so it's going to be length of Y. And then J is the number of schools, which we talked about it before. You're going to use length and then unique of the school. So it's just going to count how many different schools are there. So once you run this, you will see that on your right-hand side, you will have J equals to 100 because you have 100 schools. N is 1993, that's how many observations you have. And then the rest, which are Y, both Y and schools are vectors, length of 1,993. All right, so that's the straightforward part, I think. So once, I noticed some of you trying to delete the comma. Nope. Okay, so down here, all of this part is write the model, okay? I do want to tell you different ways of coding things. So in the past, when I was introduced to JAX or bugs, so bugs is just like similar stuff, like a package, but JAX is compatible for both operating systems, so that's why I'm using this in our class. So in the past, when I was introduced to JAX, at least the different way that I saw before is you don't write the model in your code. You actually have to write a separate text file. So that's too complicated for me. Like I have to keep track of all the different things. I find it just not like straightforward enough. So this is actually a more straightforward way. I think you can just write the model in your R code. So in JAX, when JAX work, they actually should look for a text file somewhere in the model, like in the folder that you save your model. Yeah, so this part of from line 16 to line 41, that's why the quotation mark is important. It's actually writing a text file for the model over here. But this version, like the version I'm presenting now, is just keep everything in one place so you don't get like distracted. So line 16 to line 41 is writing the model. Okay, so I will come back to this later when we describe the model, but I do want to go through all of the code for you because some of you already run all of them already. So this part I said is about the write the model. And then from line 43 to line 48, this part is actually send the model to JAX. Okay, so you see earlier, I named my model to be model.mathscore.spec, that's specification. So then you're gonna run the JAX.model, this command, to send the model to JAX. Okay, so this is what this is doing. So you see that once you send the models to JAX, you should not only tell you what the model specification it is, which is the text file, but you also need to tell R or JAX that what the data is. Okay? So the data will be the math scores, which are the Y's, the school indicator, the number of observations, and the number of schools. Okay, so that's what in the data list. You see over here? Yeah, so that's what the data list is. Okay, all right, so that's good. Once you run that, that means the model was sent to JAX. And all of this, actually only just a few lines over here, and you can combine it in one line as well, is the part that is running the model. Okay, so if you read this, so first of all, you should set seed, and then you're gonna use this coda.samples that's actually running the code, like running the MCMC for you. And the input of that, first of all, will be the JAX model. That's what we did from previous step. And then this C, the second input over here, is asking JAX to save parameter draws of those parameters. So I want all of the mu j, I want the mu, I want the sigma square, I want the tau square. So this is corresponding to what we did before using the Gibbs that we came up before. Remember, like when I wrote it in the hard way or followed the book in the hard way, we have 100 different mu j's, one mu, one sigma square, and one tau square. So back then I was saying that you should get 103 parameters. And this line, the C, and then with single quotation mark with all of the names of the variables, actually just tell R to do it for you, okay? And you specify number of iterations that you want to do and the thinning that you want to do. I put 5001 each just to replicate what we did using the regular Gibbs that we have done. Okay, so these are what the codes are doing, and the rest is similarly done as before. Okay, but now I do want to, we have about 10 minutes, but I do want to go back to line 16 to line 41, because this is the key part. This is the hardest part to write, I think, because you have to specify the model. Okay, because rest is replicable. If you see an example, you can do it again and again and again. But this part is problem specific. Okay, so let's spend, I mean, it's line 16 to line 41. So if you want to look at your computer, that's fine. It's the line number. But I do want you to think about like the way to write the model a little bit. Is it really what we believe, like in terms of what we set up the model? And how do you understand the set of the write up over here of the model? You can spend a few minutes to talk to your neighbors, I think, but you can also go back to the slides to see what we have specified. But I want us all to study the code a little bit, because that's how model specification is being done in JAX. And once, like I said, even though now we have the flexibility of using JAX, but we have to figure out how to use it in different type of modeling. So this is an example of the hierarchical model. Okay, I'm gonna spend maybe 2 minutes on this. I'll walk around as well, but you can talk to your neighbors in groups about how you understand the model, and then what's the hierarchy? And maybe I can pose one more question. What if I want to put in one more thing on hierarchy? What would you guess the code would become?
Oh.
In terms of that consuming power.
Yeah. Oh, that makes sense.
So try to first one determine the prior decision.
Yeah, it's not necessarily.
Yeah, well, I looked at this and I'm like, wow, right. The type of microscopics for a chain infection experiment. I was really confused.
Right, so that's a good check. So that would be part I still want to say no. I just answered sharing alcohol.
So like, we find that your style
Oh yeah. Yeah, so actually probably doesn't matter.
Well, because if you don't read concepts, I know.
It's not like one yeah, it's and I feel you're there should be something that's all right. about this as a class? Okay, guys. Okay, so first of all, I mean, you see that only the model part, like the model and then the curly bracket, all of this is specifying the model. Okay, so earlier there are a couple of questions, but let me just describe, like, not line by line, but like, I guess, box by box, what this is doing. So this is going a loop going through each observation, and we're saying that each observation is a normal distribution. Okay, normally distributed with a school-specific mean. So this is a vector. Okay, and school is a vector as well. Bracket is extract this particular element. So in here, school bracket I is trying to get the school indicator of the ith observation. Okay, and then the whole thing in the bracket is trying to tell me, okay, depends on which school. Say if it's school 1, I should get the first one from UJ because it's from school 1. Okay, so this is what this is about. And then earlier, a couple of people asked about why this inverse sigma here. So my understanding is the way that JAX is doing with the normal, you have to provide the inverse, the precision. So that's why I put it over there, and I try to name it as straightforward as I can. So I have inverse gamma square, inverse sigma square over there. So this is at the first level that we know, right? The second level is on the means, okay? So on the means, it's gonna be a loop not from 1 to n, but from 1 to j, because you only have j schools. Okay, and then each of it is a normal with a mean mu and variance tau squared, but because it takes precision, it's going to be inverse tau squared. Okay, so this is what the 2 levels are. But of course, there are some that this are pretty much like specified to make sure that everything is right. So mu, this is the prior. And then you notice that all of the number, like the prior values, I put it over here. I will address this in a minute. But the mu prior, this is the prior for, okay, so for inverse sigma square, which is a precision, going to be a gamma distribution. Okay, the sigma square itself is inverse gamma. So here I'm using gamma, so it's d gamma, and then the parameters similarly for inverse tau square. But eventually, I want to save only sigma square and tau square, which are the variances. So I use this, so POW stands for power. Okay, so that's a function. They don't take, like, write it and then take the power in -1. It doesn't work in that way. They have a specific function written for you. So it's POW. So it's going to be inverse gamma raised to the power of -1, which gives me sigma squared. Okay, and similarly, I do that for tau squared. And then in the end, the prior values that I put. And then of course down here, say here, just reminder here, when I try to run the MCMC code using the JAX, these are the parameters I want to save. So you need to be consistent with the names. So don't get yourself confused. And sometimes it might be easy to make mistakes. So earlier, a couple of other comments, Eli was asking, like, why, say, like the order, say like the mu, like mu null as sigma square, sigma 0 square, etc. So to be honest, I think ideally it shouldn't be here. It should be something even outside that I can pass to the model, because I want to make it more adaptable. I want to change with different parameters, right? So to be honest, I just haven't figured out how to do it. So I lived here and it worked. So that's how it is right now. But I think this is one way we can think of how to improve it. I don't think so. Right, it doesn't. I think once it's in the model, it doesn't matter, because otherwise it wouldn't even run, right? But on the other hand, I said, because I couldn't replicate results, so maybe this is problematic. I don't know yet, but this is my, like, I guess, request or like hope for all of you to figure out, like, you can run the code and you see that it's pretty fast, just, and it's done. And but unfortunately, it's just different from what I can get from this. Yeah, you see, like that. It's gone. But anyway, right. So say like I can plot things in this way. Sorry, not this, but say here, I can already tell that my results are different. And I mean, they can be slightly different. That's fine. But I think for mu in particular, it's just very off from the whole analysis from the regular Gibbs sampler. So I keep all of the similar code back here, but of course, because now things are saved differently, so you might see that, say, instead of like the MST matrix that I have, I only need to get the mu from the first column, not have to call, like it's more complicated, but this is the standard code. You can just follow this and you can extract all of the vectors one by one. But my hope is for you to go back, two things. First of all, study this and make sure that you understand and then run it and try to figure out why say like the mu estimators are so off from the actual ones. And another thing I want to ask you is so remember, we said that now this is one single sigma square, that you assume that all of the sigma squares are the same. But one extra flexibility that you can introduce here is to make that be school specific as well. Okay, so I would like you to try, because now, I mean, deriving it, the last section of the textbook talks about it, and they provide code, but I would like us to try to think how to change the JAGs to make sure that you have one more layer of this analysis, because in theory, it should be pretty straightforward. I mean, probably just one more thing over here, and then put in the prior in the right order. But I would like all of us to try. I was in an email about this as well, just to give instructions, but that will be what you need to do by Monday next week. Okay? All right, cool. Yeah, sorry about it. I ran over 2 minutes, but good, okay.